There is a pan in your kitchen right now. You have used it hundreds of times. Food doesn't stick. It's easy to clean. You bought it for $25 and never thought about it again. But here is what is happening inside that coating. Invisibly, chemically, every time you cook. Above 500 degrees Fahrenheit, the surface of that pan begins to decompose. It releases chemical compounds, some of which are toxic to lung tissue. One of them was investigated as a potential chemical weapon, and the chemical used to manufacture that coating, PFOA, also called C8, is now detectable in the blood of every human being ever tested, anywhere on Earth, in Arctic indigenous communities, in newborn umbilical cord blood, in you. The company that made it knew for decades. Today, we are going to explain exactly what is in your nonstick pan, what happens when it fails, what it does to your body, and what one attorney discovered that led to one of the largest environmental lawsuits in American history. Welcome to Why Products Fail. Let's start at the beginning. What are we actually dealing with? The pan in your kitchen is almost certainly made from aluminum. Aluminum is lightweight, inexpensive, and excellent at conducting heat. But aluminum has a problem. Food bonds to it aggressively. Eggs, fish, anything with protein, stuck badly. So engineers needed a solution. They found one in a material called PTFE, polytetrafluoroethylene. You know it by its trade name, Teflon, a brand name so ubiquitous it became an adjective. Teflon politicians, lawsuits that don't stick. PTFE was discovered by accident in 1938. Roy Plunkett, a chemist at DuPont, was working with refrigerant gases when a pressurized cylinder stopped flowing. He cut it open. The inside was coated with a white, waxy substance. It didn't react with anything. It didn't dissolve in anything. It was slippery beyond anything he had ever encountered. He had discovered polytetrafluoroethylene by accident. PTFE is, by most measures, the most chemically inert organic compound ever synthesized. Nothing reacts with it. Nothing sticks to it. Its coefficient of friction, the technical measure of slipperiness, is among the lowest of any known solid. Even wet ice is not as slippery as PTFE. For 50 years, we coated our cookware with it and called it a miracle, non-stick, safe, revolutionary. The miracle had terms and conditions. To understand why PTFE fails the way it does, you need to understand one molecule, carbon bonded to fluorine. PTFE is a polymer, a very long chain of repeating molecular units. The backbone of that chain is carbon. In a normal organic molecule, carbon bonds to hydrogen. In PTFE, every single hydrogen has been replaced by fluorine. This is the key to everything. The carbon-fluorine bond is one of the strongest bonds in organic chemistry. It takes enormous energy to break. That energy is why nothing reacts with PTFE. The fluorine atoms form a dense molecular shield around the carbon backbone, repelling water, oil, acids, bases, food proteins, cleaning products. Everything slides off. At room temperature, that molecular shield is your best friend. Non-stick cookware works because of the strength of this bond. But above approximately 500 degrees Fahrenheit, and critically, this is a temperature your stove can reach in under 5 minutes with an empty, preheated pan, that CF bond begins to fracture. When carbon-fluorine bonds break at high temperatures, they do not simply disappear. They form new compounds. Carbonyl fluoride, which in the presence of moisture becomes hydrofluoric acid, one of the most corrosive substances known to chemistry. Perfluoroisobutylene, so acutely toxic, it has been investigated as a potential chemical weapon, and ultrafine particles small enough to reach the deepest tissue in your lungs. The same property that makes PTFE extraordinary at room temperature makes its decomposition products extraordinarily when it finally does break. Now let's talk about how this coating actually gets onto your pan, because this is where the engineering failure begins. PTFE, remember, bonds to nothing. So how do you bond it to aluminum? The answer is you don't, not chemically. Instead, you use mechanical adhesion. The aluminum pan surface is first roughened through a process called grit blasting, essentially sandblasting at a microscopic scale, creating tiny peaks and valleys measured in nanometers. Then a primer layer is applied. This primer is a chemically engineered mixture that grips the aluminum peaks mechanically on one side and provides a surface for the PTFE to grip on the other. It is a molecular bridge, a chemical compromise between two surfaces that do not naturally want to connect. Then the PTFE topcoat is applied in 2 or 3 layers over the primer. The entire assembly is baked at around 800 degrees Fahrenheit, hot enough to fuse the PTFE particles into a continuous film. The final product is a 3-layer system: aluminum, primer, PTFE. The PTFE is not chemically bonded to the aluminum, it is mechanically interlocked through the primer. That is a critical engineering distinction. Chemical bonds are strong. Mechanical interlocking fails under sustained stress. And sustained stress is exactly what you apply every time you cook. There are three ways a nonstick pan fails. And almost every kitchen has a pan in at least one stage of failure right now. Failure mode 1, mechanical damage, metal utensil, stacking pans without protection, abrasive cleaners. The PTFE top coat is between 30 and 40 micrometers thick, thinner than a human hair. A metal fork dragged across that surface creates microscopic cuts that break through the top coat, expose the primer beneath, and create a path for moisture to penetrate. Once moisture gets under the coating, delamination begins. The surrounding coating lifts at the edges of the scratch, like paint peeling from a car door dent. The coating doesn't just sit there looking bad, it begins actively shedding. Those fragments end up in your food. You eat them. Failure mode 2, thermal fatigue. You heat the pan, you cool it suddenly under running water. Aluminum and PTFE have different coefficients of thermal expansion. They expand and contract at different rates. Repeated thermal cycling creates differential stress at the aluminum primer interface. It is the same mechanism that causes roads to crack in freeze-thaw cycles. Your pan is doing this invisibly every time you cook. Failure mode 3, thermal decomposition. Above 500 degrees Fahrenheit, PTFE stops being a passive surface. The polymer begins to break down at the molecular level. This is not damage you can see. There is no scratch, no visible peeling. The pan looks perfectly fine, but chemistry is happening in the air above your food that you cannot detect without laboratory equipment. A pan that looks intact can be actively releasing toxic compounds. That is what makes this failure mode particularly dangerous. Let's go deeper into the adhesion science, because this is where the fundamental engineering compromise lives. The primer layer in your nonstick pan has to accomplish something essentially contradictory: bond to aluminum on one side and grip PTFE on the other, despite the fact that PTFE bonds to almost nothing. Manufacturers solve this through what materials engineers call mechanical adhesion. The grit-blasted aluminum surface has a surface roughness measured in nanometers. The primer fills these nanoscale valleys and sets hard, physically interlocked with the aluminum peaks. The PTFE top coat then bonds to the primer through a combination of mechanical interlocking and van der Waals forces, extremely weak intermolecular attractions that only operate when surfaces are in very close contact. The van der Waals force here is the weakest link. These forces are distance sensitive. They drop off rapidly as surfaces separate. Any mechanism that introduces even nanometer scale separation between the primer and the PTFE reduces these forces rapidly. Once the van der Waals adhesion falls below the stress the coating is under, delamination begins, and it accelerates. Delaminated edges create stress concentrations that lift further coating. Water penetrates further, more delamination follows. The engineering lesson: a system held together by the weakest of all intermolecular forces, applied as a nanometer scale film to a surface that thermally cycles repeatedly, is not a system designed for indefinite longevity. It is a system designed for a useful life, after which it fails. The question is, what happens when it fails? Let's talk precisely about what is released at different temperatures. Below 300 degrees Fahrenheit, normal, gentle cooking, intact PTFE is considered essentially inert. Your scrambled eggs at low heat are not the problem. Above 500 degrees Fahrenheit, PTFE begins to decompose. Ultrafine particles are released, particles small enough to bypass your upper respiratory defenses and reach deep lung tissue, the alveoli, where gas exchange happens. PTFE decomposition gases begin forming. Above 570 degrees Fahrenheit, carbonyl fluoride appears, which reacts with moisture in your airways to form hydrofluoric acid. HF is among the most corrosive substances known. It penetrates skin instantly. It binds calcium in blood, disrupting cardiac function. Above 660 degrees Fahrenheit, perfluoroisobutylene forms, so acutely toxic that concentrations in the parts per million range cause severe pulmonary edema. The lungs fill with fluid. Military toxicologists have evaluated it as a potential incapacitating chemical agent. The syndrome from PTFE fume exposure in humans is called polymer fume fever. Flu-like symptoms: chills, fever, body ache, chest tightness. It typically resolves in 24 to 48 hours. Birds do not recover. Pet birds, parrots, cockatiels, canaries have died in kitchens across the world from overheated non-stick fumes. The connection between non-stick cookware and avian death is so well documented that it has its own name in veterinary literature: PTFE toxicosis. A pan overheated for even a few minutes can kill a bird in a room adjacent to the kitchen. And a 2023 study found that a heavily damaged PTFE pan released between 1,300 and 23,000 microplastic and nanoplastic particles per liter of food per cooking session. You are eating PTFE. What is fully characterized is what came before the PTFE, the chemical used to make it: per and polyfluoroalkyl substances. PFAS, over 12,000 distinct compounds. They all share a core property: carbon-fluorine bonds, the strongest bond in organic chemistry, a bond that does not break in soil, in water, or in your body. They are called forever chemicals, not as a rhetorical flourish, because that is physically what they are. For most of the 20th century, the key PFS used in manufacturing PTFE cookware was PFOA, perfluorooctanoic acid, also called C8 for its 8-carbon chain. PFOA was used as a processing aid. It helped disperse PTFE particles in water for application to the pan surface. It was essential to the manufacturing process. Some PFOA remained in the final product, some went into factory wastewater, some was incinerated and went into the air. Across decades of industrial production, PFOA spread globally. The Centers for Disease Control found PFOA in 99.7% of Americans tested in 2007. Today, PFOA is detectable in the blood of populations in the Amazon rainforest, in Arctic communities, in people who have never lived within 100 miles of a chemical plant. The health associations linked to PFOA in epidemiological studies include kidney cancer, testicular, thyroid disease, elevated cholesterol, pregnancy-induced hypertension, and immune system suppression, specifically reduced antibody response to childhood vaccines. In 2023, the U.S. Environmental Protection Agency set a maximum contaminant limit for PFOA in drinking water at 4 parts per trillion. That is 4 molecules of PFOA per trillion molecules of water. The EPA has stated that no level of PFOA exposure is considered safe. Now for the part of this story that belongs in a different category. Not engineering failure, human failure, deliberate. DuPont manufactured PFOA in Parkersburg, West Virginia since the 1950s. For decades, the plant discharged PFOA into the air, the Ohio River, and a landfill above the local aquifer. DuPont had internal studies on PFOA toxicity from the 1960s and 1970s. They found PFOA building up in workers' blood. They found elevated cancer rates. They found PFOA crossing the placental barrier. They classified these findings as confidential, did not report them to regulators, continued manufacturing. In 2001, Robert Bilott, a Cincinnati attorney who had defended chemical companies, switched sides. He filed a class action for 70,000 residents contaminated by PFOA. What he found in discovery? Decades of suppressed health data. Evidence DuPont knew and made a calculated decision to continue. The case settled in 2004 for $343 million. No admission of wrongdoing. A follow-up health study established links between PFOA and 6 diseases: kidney cancer, testicular cancer, thyroid disease, ulcerative colitis, high cholesterol, and pregnancy-induced hypertension. In 2017, DuPont settled personal injury claims for $670 million more. Still no admission. In 2015, DuPont spun off its chemical business into Chemours. The PFOA liabilities went with it. Chemours replaced PFOA with Genex. Genex is also a PFAS. It also does not degrade. The forever chemical problem was not solved. It was rebranded. The evidence has been accumulating for years. Consider the scale. In 2023, a study published in Science of the Total Environment tested cookware sold in the United States and found PFS chemicals in 75% of it, including pans marketed as PFS-free. Many ceramic-coated pans sold as the safer alternative to Teflon contain PFS compounds in their substrate or coating layers. The US Air Force has identified PFS contamination at over 700 military installations from firefighting foam that has contaminated groundwater across the country. In 2023, 3M company agreed to pay between 10.3 and 12.5 billion to settle drinking water contamination lawsuits, one of the largest environmental contamination settlements in American history. In Parkersburg, West Virginia, a city of 30,000 people, the local aquifer contaminated by DuPont still has detectable PFOA levels decades after the plant stopped discharging. Your nonstick pan is a small household entry point into an industrial contamination story that has been building, largely hidden, for 70 years. So what is the right response? Not panic, informed action. A non-stick pan in good condition, no scratches, no chips, no peeling, used at medium heat with appropriate utensils poses minimal acute risk. The danger concentrates at 2 points: damaged coatings and high heat. If your pan has visible scratches, chips, or peeling, replace it today. A damaged pan is actively shedding particles into your food. Never preheat a non-stick pan empty on high heat. An empty pan on high gas heat can reach 500 degrees in under 4 minutes. A $15 infrared thermometer tells you exactly where your pan surface is. Use wooden, silicone, or nylon utensils. Never metal. Do not put non-stick pans in the dishwasher. Now for alternatives. Cast iron is the original. A properly seasoned cast iron pan has a polymerized oil coating, layers of oxidized cross-linked oil that provides natural non-stick performance. It tolerates any temperature. It improves with age. It has no PFS anywhere in its construction. A large cast iron skillet costs $30 and will outlive multiple generations of your family. Carbon steel is cast iron's lighter, more responsive sibling. The same seasoning chemistry, half the weight, faster heat response. The choice of professional kitchens globally. Stainless steel with correct technique, preheat properly, use adequate fat, allow proteins to release naturally. No coating to fail, no PFS. Lasts indefinitely. If you choose ceramic coated cookware, look for third-party laboratory testing confirming PFS absence across all layers, not just the top coat. The nonstick pan is not a villain. PTFE at room temperature, in good condition, at appropriate heat, is a remarkable material that made cooking easier for hundreds of millions of people. That is a genuine contribution. What failed here was not the chemistry of PTFE. What failed was the decision made by people with access to internal scientific data to continue manufacturing the chemical used to produce it decade after decade while suppressing evidence of its consequences. The science of polymer adhesion failure is real and teachable. The toxicology of fluorinated decomposition products is real and measurable. And the corporate history of PFS, from the Parkersburg Aquifer to the 3M settlement to the rebranding of PFOA as Gen X, is documented, litigated, and on record. The next time you reach for that pan, you will understand what is underneath the surface, what it took to put that coating there, what happens at high heat, and what one attorney in Cincinnati found when he started asking questions that a corporation had spent decades hoping nobody would ask. That is what Why Products Fail is about. Until next time, take care.